and welcome to this new class. Before getting into the optimization, we do have first to better understand how an FPGA is working, also from a computational point of view. We know that an FPGA is an integrated circuit, or IC, that can be programmed to implement different applications. We know that an FPGA contains programmable logic components and programmable interconnection, but no instruction fetch at runtime, which means FPGAs do not have a program counter. In most FPGAs, the logic components can be programmed to duplicate the functionality of basic logic gates or functional intellectual properties, also known as IPs. Although the traditional FPGA design flow is more similar to a regular IC than a processor, an FPGA provides significant cost advantages in comparison to an IC development effort and offers the same level of performance in most cases. Another advantage of the FPGA when compared to the IC is its ability to be dynamically reconfigured. This process, which is the same as loading a program in a processor, can affect part or all of the resources available in the FPGA fabric, as we know. Like microprocessors, modern reconfigurable logic designs can be employed in a wide variety of applications. Application acceleration and system adaptation can be achieved by specializing the reconfigurable logic in the target system. Within this context, programmable logic devices provide an alternative growth path that allows application specialization while benefiting from the full effects of commoditization. When compared with processor architectures, the structure that comprise the FPGA fabric enable a high degree of parallelism in application execution. The custom processing architecture generated by SDXL for an OpenCL kernels presents a different execution paradigm. This must be taken into account when deciding to port an application from a processor to an FPGA. To better understand such a scenario, let us briefly compare a processor's sequential execution with the intrinsic parallel nature of an FPGA implementation. In a processor, to keep it simple, we can identify two main components: a data path and a control unit. On one hand, a data path is a collection of interconnections, functional unit or FAUs, such as arithmetic logic, units or multipliers, that perform data processing operation, registers and buses. Its inputs are control points, while the generated outputs are signals. On the other hand, the control unit is a state machine meant to orchestrate operation on the data path based on desired function and signals. A processor, regardless of its type, executes a program as a sequence of instructions that translate into useful computation for the software application. To do this, the processor has to be connected via a bus to a memory. The bus, from an high-level perspective, can be seen as composed by three different types of lines: control, data, and addresses. The application that has to be executed on a specific processor is transformed into a sequence of instructions by processor compiler tools, such as the GNU Compiler Collection or GCC. These tools transform an algorithm coded in a programming language such as C or C++ into a series of assembly language constructs that are specific to the processor we are going to use to execute our application. To make it simple, the job of a compiler is to accept as input a sequence of C instructions, as in the following example: A equal A plus B plus C, and transform them into the sequence of assembly instructions, as in the picture. The two assembly instructions above define the addition operation to compute the value of A in terms of the internal register R01, R02, and R03 of a processor. The first instruction, add R01, R02, R03, is basically telling us that the input values for the computation are stored in register R02 and R03, and the result of the computation is stored in register R01. Similarly, the second instruction is computing the result on R01 using as input values R01 itself and R02. The first thing that we can observe is that even if in C we were working with just one instruction, its translation to assembly has been implemented by using two assembly instructions. This is because of the fixed architecture we are working with by using a processor. In this specific example, we do not have a functional unit to perform an addition of three operands. Therefore, we have to see it as a sequence of two sums of two operands each. Given this, it's worthy to mention also that the assembly code above is still a simplified version of what we do really have, as it does not express all the instructions needed to compute the value of A. This code only handles the computation after the data has arrived at the processor. Therefore, the compiler must create additional assembly language instruction to load the register of the processor with data from a central memory and to write back the results to the memory. The complete assembly program to compute the value of A is shown here in the picture. Now, the number we added before each assembly instruction is just its corresponding address. With all this information, we can see how these 6 assembly instructions can be executed on a standard processor. At the very beginning, we are setting up our architecture, and we can imagine a scenario like the one depicted in the figure, where the program counter, or PC, is storing the value of the next instruction to be executed, and with all the data and instructions stored in the memory, which is quite a strong assumption. The computational latency of each instruction is not equal across instruction types. As an example, depending on the location of A, B, and C, the load operation takes a different number of clock cycles to complete. If the values are in the processor cache, this load operation completes within a few tens of clock cycles. If the values are in the main double data rate DDR memory, this operation takes hundreds of clock cycles to complete. If the values are on a hard drive, the load operation takes even longer to complete. This is why software engineers with cache hit traces spend so much time restructuring their algorithm to increase the spatial locality of data in memory to increase the cache hit rate and decrease the processor time spent per instruction. Now, this concludes our first brief introduction to this code, and we are now ready to get back to see how the code is going to be implemented on a processor and is going to be executed.